To determine the potential savings from turning off a motor for a certain amount of time each day, you can use the kilowatt-hour formula. Firstly, understand that a kilowatt-hour, abbreviated as kWh, is a unit of energy equal to 1 kilowatt of power sustained for 1 hour. The fundamental formula is kilowatt-hours equals power in kilowatts multiplied by time in hours. Now, let's break down how to calculate the money you could save. The first step is to determine the power of the motor. Look for the motor's nameplate, where the power rating is usually stated in kilowatts. Secondly, calculate the kilowatt-hours used per day. To do this, use the formula kilowatt-hours equals power in kilowatts multiplied by time in hours. For example, if the motor runs for 18 hours a day, the kilowatt-hours used per day equals power in kilowatts multiplied by 18 hours. Thirdly, calculate the kilowatt-hours saved per day. This is found by subtracting the kilowatt-hours saved by turning off the motor for 6 hours from the kilowatt-hours used per day. The formula is kilowatt-hours saved equals kilowatt-hours used per day minus power in kilowatts multiplied by 6 hours. Fourthly, determine your electricity cost. Check your electricity bill or contact your utility provider to find the cost per kilowatt-hour. Fifthly, calculate the daily savings. Multiply the kilowatt-hours saved per day by the cost per kilowatt-hour. The formula is daily savings equals kilowatt-hours saved multiplied by cost per kilowatt-hour. Sixthly, calculate the annual savings if desired. Multiply the daily savings by the number of days in a year, which is 365, to estimate the annual savings. The formula is annual savings equals daily savings multiplied by 365 days. Here's an example calculation. Assume a motor power of 10 kilowatts, a daily runtime before of 18 hours, a savings runtime of 6 hours, and an electricity cost of 10 cents, or 10 cents per kilowatt hour. Firstly, calculate the kilowatt hours used per day. This is 10 kilowatts multiplied by 18 hours, which equals 180 kilowatt hours. Secondly, calculate the kilowatt hours saved per day. This is 180 kilowatt hours minus 10 kilowatts multiplied by 6 hours, which equals 120 kilowatt hours. Thirdly, calculate the daily savings. This is 120 kilowatt hours multiplied by 10 cents per kilowatt hour, which equals $12. Fourthly, calculate the estimated annual savings. This is $12 multiplied by 365 days, which equals $4,380. Keep in mind that these calculations are estimates and may vary depending on actual usage and the specific electricity rates. To reiterate the process one more time, consider these steps in order to determine potential savings. Step 1. Determine the motor's power in kilowatts from the nameplate. Step 2. Calculate the daily kilowatt-hour consumption by multiplying the motor's power in kilowatts by its daily operating hours. Step 3. Determine the kilowatt-hours saved daily by multiplying the motor's power in kilowatts by the number of hours it will be turned off. Step 4. Find the cost per kilowatt-hour from your electricity bill. Step 5. Calculate daily savings by multiplying the kilowatt-hours saved daily by the cost per kilowatt-hour. Step 6. Project annual savings by multiplying the daily savings by 365 days. By following these steps, you can estimate the potential cost savings from reducing a motor's operating hours. Remember to use accurate data for the motor's power and electricity costs to get the most reliable estimate. These savings can be very beneficial for businesses looking to reduce costs. Remember to stay safe when working with electrical equipment and consult with qualified professionals when needed. There are a few additional factors to consider when calculating these savings in real-world applications. Firstly, motor efficiency plays a vital role. Motors are not 100% efficient, meaning some of the electrical energy is lost as heat. The efficiency rating, often found on the motor's nameplate, indicates the percentage of electrical power converted into mechanical power. When calculating energy savings, consider using the motor's input power, which accounts for these losses. To find the input power, divide the output power by the efficiency. For example, if a motor has an output power of 10 kilowatts and an efficiency of 90%, the input power would be 10 kilowatts divided by 0.9, which equals approximately 11.11 kilowatts. Use this input power value in your kilowatt-hour calculations for a more accurate estimate. Secondly, consider demand charges. Many commercial and industrial electricity customers are billed not only for the energy they consume in kilowatt hours but also for their peak demand in kilowatts. Demand charges are based on the highest power draw during a billing cycle, typically 15 or 30 minutes. Reducing motor operating hours, especially during peak demand times, can lower these charges, resulting in additional savings beyond those calculated using just a kilowatt-hour formula. To assess the impact on demand charges, you may need to analyze your historical electricity usage data or consult with your utility provider. Thirdly, account for motor startup inrush current. Motors draw significantly higher current when starting up than during normal operation. This inrush current can be several times the motor's rated current and can impact your electricity bill. Frequent motor starts and stops can increase energy consumption and demand charges. If the motor starts and stops frequently, consider this factor in your energy savings calculations. Data loggers or power quality analyzers can help measure inrush current and its impact on energy usage. Fourthly, explore variable frequency drives. For motors driving variable loads, such as pumps or fans, installing a variable frequency drive can significantly reduce energy consumption. Variable frequency drives adjust the motor's speed to match the load requirements, avoiding the need to run the motor at full speed when less power is needed. This can lead to substantial energy savings, especially for motors that operate at reduced loads for extended periods. Fifthly, consider power factor correction. Power factor is a measure of how effectively electrical power is used. A low power factor indicates that a significant portion of the electricity is being wasted. Improving the power factor can reduce energy consumption and lower electricity bills. Power factor correction can be achieved by installing capacitors near the motor. Your utility provider can assess your power factor and recommend appropriate correction measures. Sixthly, consider maintenance practices. Regular motor maintenance can help ensure optimal performance and energy efficiency. Proper lubrication, alignment, and cooling can reduce friction and heat, minimizing energy losses. Inspect motors regularly for signs of wear or damage and address any issues promptly. A well-maintained motor will operate more efficiently and have a longer lifespan. Seventhly, consider environmental factors. Ambient temperature, humidity, and altitude can affect motor performance and energy consumption. High temperatures can reduce motor efficiency and lifespan, while high humidity can cause corrosion and insulation breakdown. Ensure that motors are properly ventilated and protected from harsh environmental conditions. Eighthly, consider tax incentives and rebates. Many government and utility programs offer tax incentives and rebates for energy-efficient equipment and practices. Check with your local utility provider and government agencies for available incentives that can help offset the cost of implementing energy-saving measures. Ninthly, consider data logging and monitoring. Installing data loggers and monitoring systems can provide valuable insights into motor energy consumption patterns. These systems can track kilowatt hours, demand, power factor, and other parameters, allowing you to identify opportunities for further energy savings. Analyzing this data can help you optimize motor operation and fine-tune your energy management strategies. Tenthly, consider employee training and awareness. Educating employees about energy conservation practices can help promote a culture of energy efficiency. Train employees to turn off motors when not in use, report any motor issues promptly, and adopt other energy-saving habits. By fostering a sense of responsibility and awareness, you can empower employees to contribute to your energy-saving goals. In summary, calculating energy savings from turning off a motor involves several steps and considerations. Start with the basic kilowatt-hour formula, but also factor in motor efficiency, demand charges, inrush current, variable frequency drives, power factor correction, maintenance practices, environmental factors, tax incentives, data logging, and employee training. By taking a comprehensive approach, you can accurately assess your potential savings and implement effective strategies to reduce energy consumption and lower electricity bills. Finally, remember that safety should always be the top priority when working with electrical equipment. Consult with qualified professionals for any electrical work and follow all safety regulations and guidelines. By combining careful planning, accurate calculations, and safe practices, you can achieve significant energy savings and contribute to a more sustainable future.